So welcome to the HKS Energy Policy Seminar. I'm Joe Aldi, and I'll serve as the host today. We're thrilled to have everyone joining us, both here in person and virtually via Zoom. Before we start today's seminar, a quick announcement about another event we have going on this week. Our colleagues at the Belfer Center are pleased to host a discussion about the 2024 winner of the Roy Award for Environmental Partnership. Our colleague Henry Lee and others will be a part of this conversation with representatives of Kim Forward, the 2024 winner. That's going to be at 4:30 on Wednesday in Malkin Penthouse. So if you're interested, let us know. We can connect you to the right website so you can register and join us for that event. But now on to our main event today. It's a great pleasure to have one of our new colleagues here at Harvard join us for today's talk. Le Chier is the Gordon McKay Professor of Electrical Engineering at Harvard John Paulson School of Engineering and Applied Sciences. Before joining the Harvard faculty this year, Professor Chier served on the faculty in the Electrical Engineering and Computer Engineering Department at Texas A&M. He is a fellow of IEEE and an IEEE PES Distinguished Lecturer and a recipient of an NSF Career Award. Relevant to today's discussion, he's a founding chair of the IEEE PES Subcommittee on Big Data and Analytics for Grid Operations. He earned his PhD in Electrical and Computer Engineering from Carnegie Mellon, a master's in Engineering Sciences here at Harvard, and an undergraduate degree in Electrical Engineering at Tsinghua. Le, it's been a pleasure having you join us over the course of this year as a member of the audience, and we're thrilled today to have you as a speaker in the seminar. Welcome.
Thank you. Thank you, Joe. I got slightly upgraded every time I come to Kennedy School because I have to dress up. So, it's a great honor and pleasure to be speaking at the Energy Policy Seminar Series. I'll be talking about something that we have been thinking quite a bit and doing quite a bit over the past few years, sort of summarized by a working paper that Professor Paul Josko and Chen Singh and I just submitted a couple of weeks ago. It really has to do with the sort of interplay of AI and power systems. Now, AI is on everybody's mind, so I don't have to remind you on that. So let's just dive right in. How many of you have used GPT or some sort in the past 24 hours? Right. So we are really getting into, after all these decades of efforts on artificial intelligence, we're getting into this era of so-called generative AI, right? So generative AI, or so-called, large language model, exemplified by the arrival of ChatGPT, but really kind of started before that in the introduction of the so-called transformer architecture, has really galvanized the entire human civilization. It took 5 days for GPT to arrive 1 million users. And as of today, actually, it pretty much stable at around 1.8 billion users on a daily basis. Now, not everybody here has an expertise on computer science or AI, so I thought I should just spend just one slide, talking about what in the world is large language. So there are 3 terms that you always hear: generative AI, LLM, or foundation model. What in the world are you talking about, right? So let me just use one slide to demystify that a little bit. Large language model or generative AI or foundation model can be used sort of interchangeably for the purpose of my talk today. What is LLM? First of all, it is a large model. What do I mean by large? It scrapes entire internet text data, entire. So we are talking about petabyte scale of text type data. Not only the training data is very large, so is the number of so-called training parameters. So the state-of-the-art open source model like Llama 3.2 has some 90 billion parameters. So it's a lot of zeros. Just imagine that in your mind, 90 billion parameters. And the more parameters you have, the more sort of deep the neural network is, right? The second one is that it is a general purpose model. So unlike in the a few years back, you have a computer vision based model for doing computer vision application, or you have some kind of an email drafting tool for helping you to draft email. This time around is one general purpose model. And the thinking behind that is that despite we speak all kinds of different languages, language surprisingly actually displays some very common structures. You speak in English, I had a cup of coffee on Monday, and then in my mother tongue Chinese, 我喝了一杯咖啡在星期一. It's actually a very similar structure, right? So there is some point to be made about training a general purpose model. I mean, and then the second thing is that we just don't have infinite amount of resources. So we better just focus on general purpose, one language type of training. And then the third one is this era has been broken down into two stages. So the industrial practice today, when it comes to large language model, is really separated into two stages. One is called pre-training. That is the Meta, the Google, the Microsoft, the OpenAI of the world, where they scrape the entire world's data set and do a very sophisticated so-called pre-training on these 80 billion, 90 billion parameters, make it reasonably well-shaped. And then they release it and let you guys do fine-tuning. So you go around Kendall Square or Harvard Square, these startup companies are mushrooming like crazy. All these are fine-tuning companies trying to do fine-tuning of general purpose pre-trained model for a particular domain of application. For example, somebody's doing that for real estate, somebody's doing that for car insurance, and somebody's doing that for deal making, and so on and so forth, right? So that is what large language model is all about. And behind all of this pre-training and fine-tuning, it really is computing. And computing consumes a huge amount of energy. So what is the scale of energy consumption that we are talking about today? So this is from the International Energy Administration, where I can find kind of the best breakdown of sort of a data center energy consumption by different applications. I just want to kind of highlight two numbers here for you. One is that excluding the so-called crypto mining, so those of you who don't know, there is this big chunk of computation devoted to one particular type of computation called blockchain or hash rate, and that is in itself a major energy consumption. Excluding the crypto, it consumes on the order of about 300 to 400 terawatt hours per year on data centers. And crypto mining in itself is consuming on the order of about 100 to 150 terawatt hours per year. Now, terawatt hour, what does it even mean? It's a dry concept. What does it mean? I want to relate with where we live. The state of Massachusetts consumes about 55 terawatt hour of electricity on an annual basis. So you can see the ratio here, right? Okay, sort of seeming to be coming all the bad news, like we're just consuming a lot more energy because of a lot more computation. What are the colleagues in Cs or computer science doing? I mean, don't they work so hard and they have a lot of PhDs there? What are they doing? Isn't the computation become more and more energy efficient? But why is it? Let me just break it down a little bit for you. Let me start from the blockchain side. It is not to say that it is not true that we are just being dumb and sit there doing nothing and just let the computation go. Actually, there's a lot of innovation and research happening every day and night on pushing the energy efficiency frontier. So if you look at, so it's a good, in the context of crypto mining, or more precisely, Bitcoin mining, they do only one type of computation that is called hash. Hash is a mathematical calculation, and they have special purpose computation to run this hash, and they kind of define it as a hash rate. So there is a very easy quantifiable building block called hash. So a good way of measuring the energy efficiency is to look at per hash energy consumption, right? So per hash energy consumption, in terms of this yellow line, has been going down steadily, which means that there's a lot more innovation, a lot is happening on getting on a per computational basis a lot more energy efficient. We're using less energy on a per hash basis. But the amount of hash rate, the network hash rate, is growing at a much faster rate. And then if you do the simple math of multiplying these two together, what you get, particularly in the case of United States, is that there is a sort of a 20 times, not 20%, 20 times increase of electricity consumption in the United States just over the past 7, 8 years in terms of Bitcoin mining, right? So that's on the crypto side. It's a little easier to quantify the building block. Now, what about the AI side? So we talked a lot about what is the building block. So our group have been thinking a lot about that. And that's probably the best curve I can come up with, which is the building block of training this large language model is a technical jargon called tokens. So if you don't know what is token, it's kind of like the block of the text that you try to do this pre-training. So roughly the number of token is equivalent to the number of computational complexities. And then a good way of measuring the energy efficiency for AI training is to say, what is the per token computation consumption in terms of energy? So that's the joules per token on the right-hand side, y-axis, right? So as you can see, you look at the state-of-the-art NVIDIA chips, right? So right now we are at NVIDIA Hopper stage. And they're going next to the NVIDIA Blackwell, right? That's absolutely the frontier right now. As you can see, the computer engineers, our friends in C's and other places are pushing this very hard, right? This energy efficiency is becoming more and more, doing a lot, the same amount of token computation with a lot less joules, meaning energy. But we just come up with just insatiable amount of demand for intelligence, right? One day we want somebody to draft email for us. The other day you want to have some kind of a robot to clean the house for us. The next day you want to say, oh, let's have a general agent. Have you guys heard about Manus? It just came like 2 weeks ago. It's kind of like the first kind of agent type AI tool where it's like you can just sit there and sleep, and then this Manus is creating a virtual computer and doing all the data crunching and stuff like that for you. It's like, oh, solve a problem for me, and then they will go do this research and come up with the code and give the answer and present for you a PowerPoint slides, right? So, and this is just this incredible amount of innovation happening on a weekly or daily basis, right? And all that is basically meaning it's outpacing the rate that we are getting from the per computation energy efficiency front. So altogether, we're going to consume a lot more energy. Now, very natural question, people would say, hey, don't you heard about DeepSeek? What's going on in DeepSeek, right? You must have heard about DeepSeek on the news, but I don't know how much you know about DeepSeek. It basically is kind of like a lightweight version of pre-training model that a group of 20-year-old entrepreneurs came up with using a lower-end computational architecture, actually not the high-end computational architecture. What I want to say here is that just imagine, it's kind of like those days when you were first being introduced to iPhone and stuff. When the technology become more cost effective, your demand for that technology suddenly goes a few more folds, right? So I think in terms of the energy consumption implication, it's still early. I mean, jury is still out there, but my hunch is that we're going to see a lot more decentralized, smaller scale, but together a lot higher amount of energy consumption coming from the AI side. Right? So this is, I think, a very unique time that we start to think about these issues. Now, AI is transforming every single sector. So why should we kind of talk about interplay between AI and the electric power sector? I think the reason is sort of a self-evident in the sense that AI in itself needs a lot of power, right? So that's sort of how we prepare the grid ready for the AI. But on the other hand, the grid itself can also be modernized by this tremendous amount of generative AI LLM capabilities, right? So it's a two-way street compared to most other sectors where AI is sort of just doing one-way street of modernizing that particular sector. So that's sort of I think is a unique challenge, but also a very exciting opportunity for folks in this room, right? So I kind of break it down from a time scale perspective to talk about issues related with, in my profession on operational issues, and then in planning issues, or in my AI colleagues' language, it's on sort of scheduling or siting issues, right? And the key idea here is that how do we make this a machine that actually can run in tandem, right? And let me just kind of break it down into two pieces, one on the operational side, what the challenges are, and one on the planning side, what the challenges are. Have you ever seen this chart before? This is the state-of-the-art AI training power consumption. Okay, this is the y-axis here is watts, and x-axis here is minutes lapsed. So this is the nodal level power demand for the state-of-the-art Llama, Meta Llama 70 billion training using the state-of-the-art NVIDIA GPUs. So if you are an electric power engineer, you look at this, what do you say? There's a lot of ramping going on here. It reminds me of solar generation, right? So now this is 1 unit, right? You scale that by 1 million, that become a data center. And we're talking about megawatt or tens of megawatt or hundreds of megawatt of ramping capability needs, right? Is it a small deal or is it a big deal? Maybe it's a big deal, right? So this is 1 unit, 1 GPU. Yeah. Right? So there's a lot of intrinsic physical dynamics that we are still trying to get our hands on, right? And in fact, I think I'm organizing some 20 Harvard students and faculty to go down to Holyoke on Wednesday. Part of the trip is to see ISO New England, but then students has a great idea to tag along that to go and see the Massachusetts Green Computing Supercomputing Center there, which is just next door to the ISO New England. So we're going to see that on Wednesday. That's on the intrinsic physics. We were still at very early stage of characterizing all these details, right? This is just fresh. And now on the sort of energy system side or market side, there's also a very interesting collective aggregated behavior that one needs to study. And this is a chart on January 16 of 2024, when I was still in Texas, and there was a cold front coming on. And this was sort of a interesting charts that ERCOT put about the so-called large flexible loads. So LFL stands for large flexible loads. In Texas, is roughly equal to Bitcoin mining facilities. So basically, you can look at these large flexible loads on their response in terms of the consumption. So this is the energy consumption from this, for all practical purposes, mining units. And you can see as the price change at the wholesale real-time market, and how this LFL, these large flexible loads, respond to that. A quick kind of a look into that, you might say, well, it's actually, they do respond actually, right? They respond to these high prices, but not all the time. And also the other thing that perhaps is worth mentioning is that they don't just kind of go all the way down to zero, at least in this particular case, right? So there's a lot of needs to be done to understand the aggregated behavior of these computing loads in response to grid/market signals, right? I don't think either is fully understood. So there's a lot of research. We have great students here. Whoever wants to work on this, let me know, right? So that's on the scheduling side or operation side. Now let's talk about the planning. Planning seems to be the talk of the town these days. Everybody talks about, oh, the US grid is so slow, we cannot interconnect the power grid, the data centers. So let's kind of break down that a little bit. What exactly is the situation here? The first thing is that there are just too many requests for interconnection these days. This is the scheduled load requests for interconnection. Again, here in ERCOT, I'm using ERCOT as an example, but it's very much generalizable in other regions in the country. You can see that as of 2025, this is how much load request for interconnection is. And then next year, 2026, there will be like 30 gigawatt. Just give you some perspective, peak demand in Texas is about 80 to 90 gigawatt, right? So are we talking about by 2029 or 2030, there will be basically double size ERCOT? Do you think that is going to happen or not? I don't think it's going to happen, right? But why do they request to interconnect? because these data centers are taking a chance. You know, if I submit something in Dallas, I may or may not get it. So I'm going to submit another one in Austin. So that mechanism design, Conley is looking at me because we're talking about that. This mechanism design seems to be, I don't know, not very well functioning. So we better think about that mechanism again. And not only is coming from the load side, it is also coming together on the. So then you may say, well, is this load being delayed because we don't have enough of generation? Partly true, but I would say partly not true, because you can see the number of megawatts, or sorry, gigawatts of generation requested to the grid is actually also very, very high. So in this ideal world, if you can all the generation get online, all the load center, data center get online, everybody's happy, right? There seems to be enough of a request to put online on the generation side as well. And that's actually the entire United States. So you can see the entire United States, the installed and requested queue of generation in 2023. You can see there's a lot more out there, right? So my suspicion is that perhaps there is something in the middle that is missing, and that is the grid, right? So maybe a question that we have to think about is how can we kind of speed up the transmission build out through the means of markets, right? Or some kind of a coordination. This is actually the latest 700, and I believe this is probably the highest now in the country, 765 kV transmission line being built in ERCOT region. As you can see, they're proposing kind of like they call CREZ project version number 2. CREZ stands for Competitive Renewable Energy Zone back in the late 19 and early 2000s, where lots of the wind farm in Panhandle area got connected through that project. Now they're sort of thinking about upgrading that backbone to 765 on top of the 345 kV line. So that seems to be exciting development, but can we do it for the rest of the country fast enough? And what is the way to do it in a way that it's sort of a market compatible, right? That's the big unknown there. So I think these are really very, very challenging, but also exciting problems to work on. So let me just sort of also give you a sneak peek of what we have been doing in terms of concrete research along those lines, just to illustrate some sample opportunities and really sort of open up for your discussion and comments. Right? So I'm going to focus on something we have been doing on the scheduling side. How many of you have been to a data center? Only very few people, huh? Okay, let me just play this is the world's largest crypto mining data center, located in Rockdale, Texas. So just I want to have I always say for you, like seeing is believing. So let's see it.
Hi, my name is Pierre Rochard. I'm the Vice President of Research here at Riot Platforms. We're here at our Rockdale facility. We've got guests from ERCOT and from Texas A&M University. We're going to show them around, show them what an industrial scale Bitcoin miner looks like. We're at Building D. We're visiting this building because it's an air-cooled building. So this is a great example of the world-class engineering we have here at Riot. We're in Building F, an immersion.
So you probably saw that the previous screen that you see is like lots of black dots, right? Every single black dot is 3.5 kilowatt. You do the math. The total site is 750 megawatt. I think the city of Boston is probably 750 megawatt, right? Or maybe a little bit more than that. Okay.
Cooled building out here in Rockdale. We want to show to ERCOT and Texas A&M what the cutting edge of the industry looks like in terms of cooling technology, really highlighting the quietness of this building, as well as the improved efficiency and durability of the equipment. An important aspect of industrial scale Bitcoin mining is participating in grid services, so that when there's a lot of stress on the grid, we're able to power off buildings like this one, give that electricity back to the grid. What I really enjoyed about this visit was getting to hear the different perspectives,
So I think, yeah, you got a sense of what it looks like. So in the meantime, I was kind of asked by the CEO of ERCOT saying, hey, tell us what to do to lower the peak. If you look at this is the peak demand in Texas over the past 10 years. You look at this and you feel like, is it like Vietnam or somewhere where the rate of change on the peak demand is so high? That is, unfortunately, that is true. I guess for a number of reasons, more people coming to the state, more industry coming to the state, and people are buying and building larger houses and so on. So all these together sort of come with a need of kind of a breaking down the peak. So a very natural kind of a research question I was thinking about is that what exactly can we do to tap into that flexibility that crypto mining can offer? And how much are they already doing that on a day-to-day basis, right? So thanks to the partnership with ERCOT, we were able to get some real-world data. So this is sort of I think it's probably the first of its kind, looking at the real data. I just want to highlight two numbers here. So again, this is a correlation coefficient. It's not causal analysis. It's correlation coefficient between one particular time series vector with another particular time series vector. Here we are comparing, I want to highlight these two numbers. One is comparing the the non-mining loads, basically the residential houses or industrial or commercial buildings. Look at that with respect to the system-wide net load. So in our jargon, net load is defined as the total demand minus the renewable generation. So the idea is that the renewable is kind of a good thing, and we want to take them all. So why don't we just subtract it from the total demand, and we call it net load, and that's what the rest of the supply stack needs to balance off, right? So look at the non-mining loads and the system-wide net load. What do you see? 0.971 correlation coefficient. It basically means that when the grid is stressed, so is your household. So is a university campus. So is an industrial facility. Because when the grid is stressed is when everything is very hot. I want to turn on my AC. Air conditioning was 30–40% of the consumption. So everybody wants to crank up their AC. So naturally, so you're going to consume a lot more during those peak hours. So that is what this number is about. And you look at these mining loads, for whatever reason, their behavior seems to be suggesting that when the grid is stressed, they pretty much shut off. Because the correlation coefficient is rather negative, right? Again, it's not a causal relationship analysis. People can actually look into that, and we can do some really cool research and trying to understand what is motivating that. But I think it's sort of a combination of the fact that they can make money off of it, and also sort of ERCOT demand them to do something, and they kind of wanted to kind of be portrayed somewhat to be a good citizen of the grid, right? So let's sort of just go under the hood a little bit more. So we actually visualize this for you. Sorry, this is actually not the that's okay. The next slide will show that. So this is kind of is a snapshot of the size of the mining loads versus the electricity price in a color contoured map. So the color here is showing the real-time wholesale electricity price. The size of the bubble is showing how much and where in a zonal basis these so-called large flexible loads are located, right? So if you know a little bit about geography, this is Rockdale. This is where my house used to be. Right? This close. So it's in kind of my backyard, so I better study this. So, because this is also one of the large companies, they actually are on the public. So I kind of digged into their quarterly financial report, and this is what I found. I am no financial expert by any means, so I'll just leave it to you and let you read it. But my sort of a simple digest on this is that in that month of August 2023, this particular company actually sold Bitcoin and made about $8.6 million, whereas the power credit plus the demand response credit amounts to about $32 million. So you're like, is this a Bitcoin company or is this an energy company? Now, you can talk a lot about why, I mean, this particular company happened to secure a very long-term, big chunk, low-priced contract during the middle of COVID when nobody wants to power, and then they just reverse it and sell it. I mean, do you blame them for that? So there's a lot of things under the hood, right? So, but at least you show this intricacy of this coupling between what's going on in the financial world, what's going on in the energy world, and what's going on in the computer and AI kind of a world, right? So, and then building upon. These are like the units, the computer that they deployed. Yeah, so there's black dots that you visualized, right? So, and then we did a little bit more kind of a study into sort of taking all this data and then couple that with a grid model and trying to sort of understand on the operational as well as on the reliability perspective, what exactly are these data center, in particular in this case, it's crypto mining by data center, going to affect the grid operation and planning on a sort of a more futuristic scenarios. Three things we kind of care about most, at least when I talk to power engineers, is number one, reliability, and number two, carbon footprint, and number three, the wholesale market price. So we study exactly these three. So in terms of the reliability, so reliability is of paramount concern for power grid operators and planners. One thing that perhaps is worth mentioning here is that if you are modeling this data center as firm demand, you are in for big trouble. So the reliability is really deteriorated. But if you model this data center either as a fully flexible load or even just as a partially flexible load, in the sense that you just allow them, you only require them to be flexible between 2 p.m. and 8 p.m., 6 hours a day, the impact on the reliability can be significantly damped. And in the case of fully flexible demand, they can actually be a positive contributor to the system reliability, because in a future scenario where we have lots of renewable supply, actually that being able to turn it off in itself is actually a big asset for the grid. So that's on the reliability side. On the carbon footprint side, one of the kind of a contemporary study was a study done by the University of Cambridge Center for Alternative Finance, where they had a Bitcoin mining index database that was assuming a very generic, in this particular region, we have this much of a source of power supply. We're going to just basically using that as the average carbon emission intensity, and that's the number. We took a little bit more deeper dive into understanding the subtlety of electrical locality of different data centers and their impact on the carbon footprint. So we chose different locations for studying, including the ones that were closer to renewables, the ones that are lower price, or some other ones. The overall kind of a takeaway from that is that on a per computational basis, meaning on a per megawatt hour consumption basis, the carbon intensity of that particular data center vary as much as 3 to 4 times depending on where you are located, electrically speaking, not necessarily geographically speaking. What I mean is that how closeless are you in terms of the connection to the main grid, and how strong is that transmission grid is. So location matters in that sense. And then sort of a similar message for the market wholesale price impact, depending on if you model them as firm loads or not, you're sort of really seeing a very significantly different impact on the price behavior of having this data center versus not having these data centers. In the case of firm loads, the impact on the west part of the state is significantly high in this case. On the operational side, there's something more subtle that people typically, at least in the policy arena, don't talk about, but I think it's actually worth mentioning. and that is the transient and the behavior under disturbances of these data centers. So that, I mean, the first thing, what is transient? So, let me show you an example. Here's an example actually happened in the real world, where there is a fault in West Texas, and nearby that fault, there's a lot of solar farms and wind farms. So fault basically means that like a tree touching the line, or some kind of a short circuit happened that it creates some temporary disturbances of the grid. What happened is that that for some reason triggered this data center to also trip off of the grid. Now, if you're talking about tripping your house off of the grid, no big deal. You have a small impact. But if you're talking about 200, 300 megawatt of demand tripping off of the grid, that's kind of becoming to be a big deal. So there's a lot of strange, interesting behavior that people are recording on the way that data center would behave when grid disturbances happened, right? So a question for the grid planner as well as for the data center developer is that what should be the proper protocol of integrating these data centers on the grid so that it's not a lose-lose scenario, but it's a win-win scenario, right? And the first thing that one needs to do is to figure out what in the world is their impact on the so-called electromagnetic transient process, right? So we did exactly that. We actually built this and we studied that. So there's a programmable power source. Basically, that's kind of an equivalent of a grid. We mimic the grid and we supply that to this S19 Pro, which is basically a state-of-the-art, was a state-of-the-art mining unit. And then we study how they behave if the grid has a fault or not, right? That's pretty cool. And you take it under the hood, that's actually, so this is as close as you get in this slide about in this talk about AI and computing. This is the real computing going on right here. But what's behind that is this electrical circuit. So that's kind of our bread and butter. So we try to model this and try to study what is going to be their behavior if the circuitry does look like that, right? So long story short, it does not comply with today's grid interconnection code, right? Notably, the IEEE 1547 code, they require this data center to be online for at least this long. They require them to stay online before tripping for this long, but the lab testing told us that this mining unit can only stay for this long. So there's an 18 times time difference. So what does it mean for the policymakers? It means that you have to kind of put a more stringent requirement on the grid interconnection code. Now, what does that mean for business developer? It means you need to spend more money. But there's an easy solution and there's more sophisticated solutions. The easy solution is to put on some UPS, right? Uninterruptible power supply. But that may be the more expensive solution. The more sophisticated solution is that you put a bunch of supercapacitor with some smart controllers. And if someone wants to do a startup, talk to me about that, right? So that's kind of what we are doing there, scale it up for the grid scale study and so on. So that's sort of on the operational side. I said this, maybe this animation might work. So let's see if it works or not. It doesn't. That's okay. That's sort of on the operational side, some of the challenges. I just want to also highlight one very interesting, very new study that we are doing now for the planning side. As we all know, data center planning has been a big kind of a delaying factor. So can we kind of harness the power of large language model and actually speed up these planning studies? So Alban, all bets are on you, okay? So this is sort of a sample study we are doing. Like this is the real grid. Like this is actually a not fake grid. This is a real grid, these purple lines. And then if you are a data center developer, you are faced with 4 locations, A, B, or C, or D. Each location is a candidate site for building a hyperscaler. Where would you place your $1 billion in? So there's a number of considerations. Electrical connectivity. Another thing that people have not talked about is the water access capabilities. Water is a big thing, right? So you have to actually connect with these aquifer storage and recovery capabilities. And then what is their economic development of each of the counties, and what is the utility structure? Are they co-op? Are they munis? Are they actually big ISO? I mean, big IOUs, right? So all this, is something we are developing right now as a sort of a large language model powered tool for planning acceleration, right? So that was the former chairwoman of the PUC Texas, and that was the senior VP and CEO of ERCOT, where we were presenting this to them. So that's about how we kind of prepare the grid sort of for all these interesting challenges that data center arise to. I want to just spend about 5 to 10 minutes talking about also we as a recipient of the capability of AI, how can we actually modernize some of the actions that we do on the electric power sector? I was sort of motivated by an invitation. I had the honor to participate in the OSTP roundtable discussion on AI for energy, and Department of Energy, to their credit, actually published this 400-page report called AI for Energy. If you have not read it, I encourage you to take a look at it. So, just 1 year seems to be ancient in this AI world. So that was exactly 1 year ago. And the GPT was just kind of on the horizon. And we're like, okay, why don't we just test it out? See, helping the power engineers figuring out what can large language model do, and then maybe more importantly, what can large language model not do very well in the power and energy application. So that's basically this paper that appeared last summer, late summer in June, on this topic. It kind of summarizes everything on the capabilities as well as the weaknesses of today's large language model and mapping them to various different use cases in the power and energy domain. So you can see the low-hanging fruits, as everything else, is always kind of the load forecasting or renewable forecasting, like time series forecasting. But there are some also not so low-hanging fruits. I'll just walk you through some of these. This is the load forecast, right? So load forecast, you're like, why do you do large language models to do load forecast? Isn't load forecast supposed to be numbers? Language supposed to be text? Yes, you're right. So we actually have to do a bit of a embedding there. We actually embed this sort of, you can see, zeros to A, 1 to B, this weird change. But surprisingly, actually, they did a fine job, actually. This is, again, 1 year ago. 1 year has so much has happened. But as of 1 year ago, the mean absolute percentage error of using this GPT suggested model, but you have to kind of force a more advanced version, not a linear regression, but more of a nonlinear regression model. And then they get to the order of fine-tune the GPT on the order of about 4%, right? I mean, I don't know about you, but if I present this to my ISO friends, 4% mean absolute percentage error, not too bad. Not the best, but not too bad. And then I'm kind of zooming in a little bit more on because what we care a lot more about is what happened in the peak time of the grid. So I'm sort of just highlighting 2 interesting case studies. One is on the summer peak, one is on the winter peak. So as you can see, this fine-tuned GPT model can actually do a fairly good job on predicting these are all real data. This is real data from ERCOT. And they can actually do a pretty good job in the order of 2% MAPE for the summer peak. But way worse in the case of winter peak. And that kind of explains something quite subtle for these AI tools, which is when you need a good performance, you have a good training data set. Texas has been historically not a winter peak state. So when you pull in all this historical data, you don't have much of a winter peak data. So that's why the performance was not as good, right? Now, the next thing is, very natural thing to challenge ourselves was the price. Can we actually do a pretty decent job on price forecast? As far as I can tell, the answer is no. mathematically speaking, you may argue that because the price is kind of the dual variable of this primal formulation of a linear programming problem, and forecasting a dual variable in time series is much harder. And secondly, this dual variable is a result of not only natural causes but also human causes, because there's a lot of human decision involved in the bidding process. So I think human in the loop kind of a forecasting is still a big challenge, which is good, right? You need challenges. So. And then we are also kind of doing some architectural innovation. So the building block of GPT is something called transformers, right? And these transformers are essentially this architecture that enables very nicely in the context of language. But fundamentally, all we are talking about price, electricity, energy consumption, these are all time series. So don't we have a better architectural model for just time series type of forecasting? The answer is yes. Actually, Google sort of announced this Mamba model. Again, all these are sort of happening in the past few months because this field is evolving so quickly. And this Mamba model basically has this architecture that is particularly well suited for doing this kind of a time series forecasting. So we further modify the architecture to have this sort of a dual blocks to allow us to do this temporal token, right? So if you think about language, it's sort of, there's no time associated with token, but this time series, a very natural time is associated with the token. So that seems to be working rather well in some of these time series applications. Another case which I wish we can use this less, but unfortunately we may have to use it more, is this sort of a wildfire risk mitigation. So what we did was we pretend like we are Southern California Edison, right? We look at all the historical wildfire maps, combine that with transmission line map. These are all actual transmission line map published. These are open source. Everything here is open source, right? And then you say, okay, which transmission line should I pay attention for the upcoming wildfire season, right? And then you highlight those regions in the red. And that's the area they actually highlighted. And I don't know about you, but me as a reasonably well-trained power engineer, I don't think I can come up with a better answer than this. So, so that's also displayed on the map. So another application is sort of a few shot or zero shot prompting for anomaly detection for equipment. So all these power companies, they fly drones these days across the entire territory, take imageries, and then figure out which insulator is broken and so on and so forth. For those who live in the Belmont area, you may have noticed that there was a blackout last Thursday, which lasted 5 hours to my shock. And it was a manhole blow of a cable problem. Then so those kind of things, if we can early detect some potential damage, you could potentially save a lot more time on the post blackout recovery, right? So it turns out this in-context learning capabilities that the large language model has to offer seems to be a very nice tool for this type of applications. Another one is sort of a more actually towards the language part, which is using this retrieval augmented generation. So there is a fine-tuned, pre-trained large language model, and they can do a lot of fine-tuning. And this is sort of a part of the fine-tuning. If you talk to an energy trader, if they want to enter a market like ISO New England or PJM, and if they want to figure out a particular rule of the market, what do? They go and hire Professor Hogan as a consultant, and they pay you a hefty consulting fee for doing that, or equivalent of you, somebody. Nowadays, maybe you can do that using some of these GPTs. For example, this is we feed the entire ERCOT nodal protocol, which is some 2,000-page documents, to this GPT, and we ask very, very specific question. What is the opportunity outage? I have no idea what is opportunity outage. So, but then this retrieval augmented generation answer seems to be really good. And after that, we studied what exactly do they mean by that. It actually matches quite well, right? So we still, keep pushing this boundary as we speak. In fact, we actually just submitted a paper just 2 days ago. A big part of that in the power domain, I think, is the data readiness, because a lot of the data in the power domain is either unlabeled or labeled but confidential. So how do we do pre-training or fine-tuning with this kind of a data readiness? So there are some needs to prepare the data readiness. But we also have found some very interesting good news, which is the sort of so-called scaling laws. For those who have not heard about scaling law is kind of like this whole train that is powering the AI evolution, which is the more data you throw in, the more computation you throw in, you always end up having better performance. And then you kind of are always hoping that you will continue. I don't know, maybe one day they will hit the limit. But surprisingly, in the power grid context, that scaling law is so lean and so small that you can really afford to do that. And then, like, what is the quality of this generative data should look like? Because if you're fundamentally rely on generative AI, so you're going to have a lot of generative data. So what do you mean by good data versus bad data, right? It's not going to be least square. It's going to be something else. So let me just show you this. So we are actually just doing this as of a couple of days ago. And what we found is very interesting is that if we build a fine-tuned large language model for the power grid, and then we ask the following question: how much data is needed to have a good enough performance for this large language model? I don't think anybody can answer that as of now, but we kind of have a sneak peek to this. This is very fresh. Just came out a couple of days ago. Like, you can see the x-axis here is the data size for fine-tune training. It's in terms of 1,000, right? So 1024. So basically, any number here is basically means 60,000 or 80,000. So that data size, to get how much of error here, the error is represented in terms of mean square error for different tasks, for transient prediction, for renewable power forecasting, or for state estimation. One thing that is sort of promising is that it seems like training a single task large language model versus training a multitask large language model seems to be yield comparable performance. That's good news, number one, because that means that the very notion of large language model is building upon the assumption that it's a multitask capability. So it kind of validates that in the context of power domain. Good news number two is that it seems like you draw the power law fitting. Now, be a little bit more careful, the downside of the curves, the x-axis is actually logarithm, right? It's a log scale. And the y is also log scale. You can see you can almost fit a very nice linear curve here. So it's kind of a power law behavior, right? You can sort of discover for a region of the training data, there is a power law behavior. And to get a decent performance, you don't need much of a data to start with. 100K is very affordable training, a very, very affordable training, right? So that seems to be good news number two. We'll see. I think there's a lot of exciting opportunities out here. So let me just try to summarize. I think there's a lot of opportunities, but also challenges for this interplay between AI and the electric power systems. From the powerful AI side, I think the big opportunity there is how do we align the market incentive right so that the AI developers are willing and are well incentivized to provide the grid flexibility. On the challenger side, of course, is sort of this time scale alignment and interconnection request. I don't have a good answer for that, except to say that we just have to have each other talk to each other. And for the sort of AI, or in particular large language model for the power domain, I think the best way I can describe that is that you really can think about it as a co-pilot, not a pilot, but co-pilot. To handle a lot of these time-sensitive advisory roles in a daily operations. And the safety guardrail is a big challenge. As of now, there's no safety guardrail on the outcome of any AI tools whatsoever. So if you say, do this, you will not have a blackout, don't trust that, right? So, and data privacy is another major concern. I don't know about you, but at least for me, I seem to have just give up on my data privacy. I just ask GPT to polish my email every day. Like, because I'm not a native speaker, sometimes my English may not be so good. So I ask a GPT to polish it. And, they know a lot about me. So. But what can I do? I mean, well, I need somebody to help us design the privacy preserving GPT, right? So I think it's a beginning of a new era, very exciting area for a lot of room to play for people here. In particular here, because very few places you see this technology to policy bridge so closely built as Harvard has to offer. And with that, I also would like to to review a very exciting initiative called PI, Power and AI, which is sort of our way of thinking about defining some of the research challenges and the research agenda in this area. We are actually very pleased to have a research symposium, mostly bringing the industry leaders to campus on the 20th of May, followed by a short course teaching all the AI companies how to interconnect to the power grid and teaching all the power engineers how to run large language models on May the 21st. And that's sort of the overarching agenda for the research, hopefully, which is how can we achieve a sustainable electrification in the era of AI. It needs a lot of different stack of expertise. I think Harvard is very uniquely positioned to tackle many of these issues, and very much excited to be working with you all. With that, I want to thank you and appreciate your time and interest. Yeah.
Thank you so much. We'll open it up for questions from the audience first. I'm not surprised my colleague Bill Hogan has a question. Let me go to you first, Bill.
This is terrific and exciting stuff, and I'm very interested in this aligning incentive comment that you made to try to get these things. One of the things I didn't see in the slides is an example of misalignment. The way they collect for paying for the existing grid system is a mechanism known as 4CP, which is the critical peak periods, critical peaks during the ex post measured, and then they assign the cost of the grid to those critical periods. And you ask yourself, well, is the grid most stressed during the system peaks? The answer is no. That's the misalignment part of the problem. It's actually stressed when there's kind of a much lower level because then you're flowing from cheap places to expensive places as opposed to using everything. That's a misalignment, and it then creates the incentive for people to take action in order to make sure they don't show up in the critical period calculation, like these guys. And the number what doesn't show up as revenue, it shows up as costs avoided that they don't have to pay for being connected to the grid. And I think it's actually maybe the dominant number in that story there. So that would be something worth looking at.
4CP, yeah. So thank you, Bill, for raising this issue. For those who don't know, 4CP means for coincidental peaks, and is a way that the grid operator device as a mechanism to avoid you using to incentivize you not to consume when the grid is peaked. That particular 15-minute slot in that month, right? The way kind of roughly it works is that if you happen to be consuming in that particular 15-minute slot, then you are going to pay a proportion with respect to everybody else, the entire month's transmission and delivery cost. So the 4CP. And so put the sort of a money side into context. If you are talking to a data center like these guys, their 4CP charge can be sometimes on par with their energy charge. So you have a big incentive not to consume during that particular 15 minutes. So you want to duck down when that particular peak happens. Of course, the key challenge there is uncertainty. If we are now on July 15, nobody knows when the month of July's peak would have been, right? So there's a lot of a kind of a game theory, strategic kind of a decision-making process. It's a business. People actually make money out of these advisory roles. But I think the more fundamental question there is, I think you pointed out very importantly, is that you can't use an operational or short-run type of variable cost kind of mechanism to incentivize long run kind of a construction or planning cost. And Conley and Chen and a few others, we have been kind of messing with this question for a while. We hope to come up with some answers in the next few months. So.
It's a fantastic presentation. At the beginning, when you were trying to highlight, you talked a lot about blockchain or crypto mining. Was that really? But yet the talk is around generative AI impact and on the grid. Are you doing that? Did you do that analysis with crypto as kind of a sit-in for where you think load demand will dramatically increase with?
It's chronological. So about 3 years ago, I started to get phone calls from these crypto miners and say, "Oh, do you know where I can get power contracts?" I'm like, I don't know. So it's chronological in the sense that these are the early emergence of computing loads in the grid, at least in the US context. The birth of generative AI, starting from late 2022, early 2023, has really begun to accelerate in the subsequent months. We are, as we speak, Subir is sitting there. We are actively looking into the sort of different kinds of power consumption of different kinds of generative AI tools and capabilities. But to my best knowledge, they have not reached to the level where they can kind of play big in the wholesale energy market yet. I mean, but we are kind of at the frontier. Like you go around Kendall Square or Harvard Square, there's some startup popping up right now talking about AI data center flexibility provisions. So we are just right at the tip of that curve right now. So yeah.
Thank you so much. This has been very enlightening. I'm Karen Clopton. I was the Chief Administrative Law Judge for the California Public Utilities Commission. So I'm concerned more, as they say in Texas, about the tail wagging the dog. You asked that question when you were showing the crypto mining companies' profit margin and then what they're getting from energy credits. So my question to you has to do with AI, which some would call plagiarism software, right? Because generative is not necessarily
I'm not sure about that.
might not be innovative, but there's some who do call it that. The other issue is, what is the hallucination rate that we're looking at? What is the carbon footprint of the AI being used to improve the grid? And how is this calculation, how does that go into companies who, like OpenAI, that also own, Sam Altman also owns nuclear generation companies? So is it an energy business or is it this other thing? That's my question.
So you have raised a number of points. I do see that these computing facilities are going to continue to offer, and perhaps increasingly so, offer both AI services as well as energy services. Just like any other industrial sector, right? This building is serving people living in the building. But if you do it in the right way, aggregate in the right way, this building can also be collected to provide some kind of a responsive grid services to the wholesale level energy market. So I certainly see that AI, or in general, computing industry going in that direction. That's I think is a good thing, right? You try to align your service to the end users. You're also trying to be a good citizen of the grid. Now, in terms of their carbon footprint, it is still a very early stage. There's some kind of a white paper out there, a number of white papers studying about sort of a carbon footprint of AI. I won't quote any of these because I haven't fully critically assessed any of this yet. But it certainly is an area that you are going to have an increasing amount of carbon emission because you're using increasing amount of energy, and unless we have 100% clean energy, we're going to have some kind of a carbon footprint. So So it's a trade-off between how much of a intelligence quest that we as a society need to, we are looking for versus what is the environmental impact. At least as a very first step, as you very well put it, that the carbon should be part of on the decision makers' radar, right? So it's not just AI arms race; it is also a trade-off between AI and the overall environmental impact, right?
So I want to go back to a term you brought up earlier, and you said if you really focused on firm power as opposed to having some flexibility here, it makes it really hard. You do see quite noticeable, if I recall correctly, quite noticeable price impacts in the wholesale power market. I'm curious, as we sort of think about the evolution of AI, when we think about like large companies, we hear a lot of them saying we want firm power. It's why Microsoft is restarting the unit at 3 Mile Island. But having said that, Microsoft is going to have a lot of data centers. They're going to be all over the country. Does that give them that kind of flexibility then to think about whether it's a local stressor or just prices in the local markets, which might be a function of some local stressor or just other demands beyond, say, a natural disaster stress or what have you? Does that give more and more opportunities here when we think about this from the AI service standpoint for a major company to try to optimize across a portfolio of data centers?
So Joe, that's a great point. I would like to further build on your point, saying that it is really both intertemporal as well as interspatial flexibility that this AI data center ought to provide. So the example I showed here was mostly intertemporal, but equally important is the interspatial shuffling of the job, if you wish, right? The good news is that there is sort of this architectural evolution. So if you're thinking about sort of the transformer-based architecture, unfortunately, this, if you talk to some of my colleagues who know way more than I do on the computing chips, like if you're doing the pre-training of GPT, don't mess with me. I want a firm power, and that may last. Subir was telling me like may last hours, right? The pre-training may last hours, and that's a firm demand. But now this architectural innovation is happening, and we are seeing a lot more fine-tuning jobs popping up. And again, with this sort of a disruption of DeepSeek and other innovations, you're seeing a lot more activities picking up on the fine-tuning side than on the pre-training side. And that gives a lot more leeways on flexibility, both intertemporally speaking and interspatially. So I think we are sort of seeing that direction in a positive way. So.
Great. We have time for one more question.
But overall consumption will be higher.
Yeah.
My bet.
Yeah. Yes, please. Last question.
I'm just curious about the transmission lines. We talk about planning. How much can we be using AI to improve? Like, there seems to be certain places where transmission lines will be most beneficial. And
yes.
Yeah, what? I'll keep it brief. Yeah, but what can AI be used for that?
Right. So I happen to have a couple of former PhD students who are doing these planning studies for system operators. I call them and say, "What are you doing every day?" And they say, "Oh, we have this March, whatever, close gate. We get the yearly piles of interconnection requests in, and then we run these planning models, and then we figure out this is a reliability must-run upgrade, or is it the economics upgrade? And then we go back to the stakeholders and communicate with them, and then they sometimes say yes, sometimes say no, and then we have to redo it. So all in all, I think a lot of the time, there's two pieces of kind of a major blocks. One is the technical side, just these human hours invested on running this planning model and the studies for many, many uncertain scenarios. And those uncertain scenarios, you know that most of them will turn out to be not materialized, but nevertheless, you still have to study that. That's a barrier number one. Barrier number two is more on the sort of I would say, human to system interactions. Like one of the study plan was suggested by the ISO, and then the ISO present this to one of the developers, and the developers does not like it, or if the utility doesn't like. So there's a multi-party kind of a negotiation. Lawyers kick in, and everything get delayed. That is another big sort of a time delayed factor. I haven't figured out how to solve the second one yet, but I think the first one is a good chance we can speed up that planning studies a lot more through automated large language model simulations.
So before we wrap up, let me know we'll meet again in a week. Here we'll have our Kennedy School colleague Akash Deep for a talk about international climate finance. And finally, please join me in thanking Professor Le Chier for a fantastic talk today. That was awesome.
Thank you.